Okay, you're on.
Yeah, good afternoon, good morning, wherever you are on this planet, and welcome to our SETI Live. So today we are going to talk about a very interesting new body by David Armstrong and his team. David is a researcher at University of Warwick. Hi, David, how are you?
Hey, great, Frank. Thanks.
So David is in the UK, right?
Yeah, so in the UK at the moment.
Nearby Birmingham. And so, as I say, he's the lead author of a paper that was published in July on a very interesting target which is called TOI-849b. We do love those numbers, right? So first, before going through the details of what is this TOI-849b, and should we find a nickname for it?
So this TOI-849b is a new planet that was discovered by the TESS satellite. It's a NASA mission that's up at the moment looking at lots of different stars trying to find new planets. Whether we get a good nickname for the planet, I don't know. It's always hard to suggest these things. You can try and put something forward and hope people pick up on it, right? But in the end, they always get named after the mission. So TOI is TESS Object of Interest, which, you know.
Right. So what is TESS? TESS is a space satellite. We have talked about that in the past, right? And what exactly, how TESS has discovered this planet?
Yeah, so I can show you a picture of TESS, actually, if you're interested. There's one there. It's a NASA mission. It's a telescope that's on an orbit around the Earth at about almost a 30-day orbit. It gets out to somewhere near the moon's distance and then comes back in. And it stares at patches of the sky for a month at a time, just measuring the brightness of all the different stars that it looks at. Mm-hmm. And somewhere in those stars, we look for little dips in light when planets pass between us and the star and block out a little bit of the starlight. And that's called a transit. And it's how we've discovered most of the planets that we know about today.
So this is 849, so that means that the planet number 849 discovered by TESS?
And not quite. It was the 849th object of interest that they released as a candidate. So some of them have been confirmed as planets and some haven't. And this one has, luckily enough. And it's a very interesting planet for it, so I'm sure we'll talk about.
So this was discovered by the TESS. So TESS observed this star, which is magnitude 12. I read this in your paper, which is 750 light years away from us. So
yeah, that's right.
Far away, right? And so you have seen this small attenuation. So what? It's how many planets we know? We know 4,000 of them, even more now. Why this one is so interesting that it was published in Nature?
Sure, so there's a few reasons. So to start with, it was just a planetary candidate, and we were running a program trying to look at some of these interesting TESS discoveries and see what we could find and measure their masses as well. So that gives us a bit more information about the planets. And this one turned out to be especially unique. So not only is it, well, it's about, very slightly smaller than Neptune and very close to its host star. So it orbits it in less than a day, about 0.7 days, 18 hours. So it's extremely hot. But not only that, but it has a mass that's very, very high for that radius. So it's, like I said, it's very slightly smaller than Neptune, but it's got a mass that's almost 3 times as much. It's very, very dense. And we just don't expect to see planets this big and this dense. It's got a similar density to the Earth. Mm-hmm. So that's really what makes it unique, that and its location. Very close to the star. There's just not planets of that size that close to the star. It's a region we call the Neptunian desert, just because we see such a big gap there, and it's been a long-standing feature of the planet population. They're just very rare there for various reasons. So this is an outlier. Something strange has happened to produce this planet, and that's what makes it interesting.
Yeah, so that's something I read in this paper. In fact, most of the planets we have discovered very close to the star, like this one, they were kind of Jupiter size. Okay, we used to call them hot Jupiters. We still call them like this, in fact. This is what we call a hot Neptune, we thought, because of the fact that, because of the size. But the surprise here is that you have detected also the planet using another technique called radial velocity, and you get the mass. And from the size that you from TESS and the mass, you derive the density. Can you show us a bit what is TESS and explain to us radial velocity? Maybe you have a slide.
So the next one I can show you here is the telescope that we use to try and determine this planet's mass. So this is at La Silla Observatory in Chile. It's a 3.6 meter telescope, and inside it is a spectrograph called HARPS, which is up on the top right there. And using that, we can observe these particular stars and get a whole spectrum of the starlight. So all of the starlight split into different colors and wavelengths. And there's a sort of unique signature in that we can track. You sort of see very specific sort of absorption lines, dark bands in that. And it tells us a lot about the star as well, but we can look at those shift very slightly just as the planet moves. So as the planet moves around the star moves just a little bit as well. It's actually very, very slow, really, kind of a walking pace. And on the scale of something like a star, that's really, really fascinating that we can actually detect that. But when you see it moving, you can see these little lines just shift a little bit. And how much they shift tells us how massive the planet is. So by doing that for this star, we were able to measure the mass, and it was just sort of strangely high. We actually, when we got the first few data points out of this, we actually thought we were looking at some kind of false positive, like a binary star or something that was just going very wrong, you know, because it was just so unlikely that it would be showing a curve like this. But it turned out to be real.
Yeah, because in the 4,000 planets we know, there is very few of them for which we have the size and the mass, so the density.
It's increasing, but yeah, there's very few with this combination for sure.
It's a great way to really truly characterize those exoplanets, because we don't really know much about them beside those measurements. So what kind of measurement? What does it look like?
So we take things with this, we follow it up with some other telescopes. So I just had this one quickly. It's a survey called NGTS that's also in Chile at Paranel Observatory. And we used to sort of point again and confirm that the signal test saw was real. Mm-hmm. But once we do all that, we sort of get a series of data that looks a bit like this. So at the top, you can see what TESS originally measured, the sort of light curve of the planet. And those little vertical lines there in purple show where all the transits as the planet passes in front of the star are. Now you can barely see them if you look at them one by one like that, right? But if you sort of fold them all on top of each other and look at them combined and look in the middle at the bottom there, that's what we get, this sort of characteristic transit shape. So
this is an attenuation of the light of 2%. 0.2.
No, 0.2, yeah.
Yeah, 0.2%, sorry. It's very small. I mean, it's
tiny.
Like, it's a tiny attenuation. And that's the reason you use TESS. We send a spacecraft in space because space is more stable environment. We don't have the atmosphere and all of the light. And that's allow us to kind of measure this small attenuation.
Yes, for sure. Though we're getting much better with transits from the ground as well. So the one on the bottom right is from this NGTS survey, and that's by combining 10 different telescopes from the ground, all pointing at the transit at the same time, taking thousands upon thousands of data points that we've had to bin up just to show it there. And you can see that we can start getting to similar sort of noise levels just from the ground there as well, although it's much harder to do to start with. So we're getting better with that too. These are very, very shallow dips. I mean, a tiny fraction, like you said. I mean, when we try and do it with this follow-up technique, so when we use HARPS and try and measure the mass, we get the data you see on the bottom left there. It's this sort of sinusoidal shaped curve there, where it just goes down and up. And that's what tells us how massive the planet is.
I just wanted to mention, because you say it, on the left side, you see the speed, the radial velocity. That's the speed of the motion. So that's 30, the maximum is 30 meters per second. It's not that much, right? It's really slow pace. No.
Yeah, considering this is a star moving, I mean, it's very tiny, right? These things are huge.
So you combine this data. So we have the size and the orbit using TESS, because you know the size of the star. The star is a G-type star or something like this?
It's similar, yeah, very slightly smaller than the sun, but pretty
similar to the sun. And then on the left, you have the radial velocity, so you have the mass. And you have the angle of the orientation of the system. Combine this, and that's give you basically the size of the planet, the mass of the planet, and the density of the planet.
Yep.
All right. So what did you get? You mentioned it.
So this is what made it such an interesting object, really. There's two key things that come out. I mean, let's look at the left here to start with, this Neptunian desert that we mentioned. So that's TOI-849b there, right in the middle of those dashed lines. And you can see all the other planets in gray spread around. And in this big gap in the middle, surrounded by this triangular region, is called the Neptunian desert, because it's about the size of Neptune or the mass of Neptune, and we just don't see planets there. And you can see that this is an exception to that rule, right? There's just right there in the middle.
Just in the middle.
Which is very strange all by itself.
So when you found out this, you knew it would be a paper in Nature, right?
Almost. So there was one before this. So this one was kind of maybe Nature Astronomy we could get to that level. What made it Nature was when we also realized that the density of the object was just so high for the size of it. So this is kind of coming onto the plot on the right, which is a bit more involved. But you can see, if you look at on the x-axis on the right, that's the mass of the planet, and you can see it's quite far over to the right here. Neptune and Uranus are that little N and U you see in the middle, just to give you a comparison to the solar system. So you can see it's much more massive than those, but also a bit smaller, and we just don't see planets around there. All the planets sort of go off up to the top and out of the plot above it, all the other planets that we know about. it's actually got the same density as the Earth and sort of a composition that's much more sort of terrestrial and rocky. And just to have a planet that's that size and that massive and still have that sort of composition is completely unique, really.
So this
Even
is
more
kind
so
of a
than the
mega
desert.
Earth. It's like
An ultra Earth, something like that.
Yeah,
I mean,
3-4 times the radius of
you know,
Earth with the same density. It's a rocky planet.
Yeah,
That's really important. That's kind of the surprise here.
Yeah,
so
for
it's
sure.
not a Neptune.
No,
Right.
I mean, well, you know, you can say it's the same size, but whatever. What does that mean at this point?
Yeah.
It's closer to Earth in type. I mean, it's going to have something of an atmosphere, right? But by mass, it's a very tiny fraction, like a few percent of the planet's mass at most.
So when you got these measurements, and you got that quite quickly, I'm assuming, the observation was taken in 2018? No, 2019?
19, yeah, and we managed to follow it up a few months after it came out, I think.
So it's good to explain a bit the people how we work, because people think that we'd make discovery by being stuck in our office in a few days, but in fact, it works for a long period of time. So there was first observation with tests.
And then some candidates get released, and you try and find the interesting ones to look at, and then you point the other telescopes at these and try and confirm that they're real and interesting. And I've talked about the mass and the radius, but there were lots of other telescopes involved to check that there weren't sort of other stars contaminating the signal and things like that. So all of this came together, and by this point we're talking lots of people, right? I mean, nearly 100, I think, authors we had on the paper by the end. All these different facilities and institutes and researchers tend to come together and work as a big collaboration. And then once you've got all that data together, you have to start analyzing it. And then when you get to this point where you've got the sort of interesting parameters of the planet, you have to start trying to think, well, you know, how did it get here? Like, what happened to make this happen? And how does that relate to everything else? And that's a whole stage all by itself. So then, you know, once you've put all that together and brought all the people together and had your discussions and everything, then you sort of get to the paper.
Before we go to this, I want to remind our viewers, we are streaming live right now on Facebook, YouTube, Twitch, Periscope, and maybe another one that I forgot. Let us know where you're watching us from, and get ready. We're gonna basically take a few questions in 5 or 10 minutes. So before we continue, I just want to mention that we have people already watching us from Bogota, Colombia, from Southern California, from London. It's a small city in a country north of France. Inverness, Scotland, New Zealand, Louisiana, Sweden, Lansing, Illinois, and we have someone from Europa. So I don't know if it's the satellite of Europa, satellite of Jupiter, or that's Europa, the continent. But welcome everybody, and thank you for watching us early in the morning for people in California, and evening for Europe. Okay, so we were talking about how this bodies is quite interesting and quite different to any other non-exoplanets because of its density, because of its mass. So, what it is? What's your theory around this target?
So we have a few, right? So there's a few ways you can get to this. I mean, I think to put a bit of context on it, what you have to realize is that most of these planets, they either form like the Earth and they kind of stay quite small and they stay rocky, or they cross a kind of threshold. We call it critical accretion threshold, and they undergo what's called runaway gas accretion. They get lots and lots of gas sort of piling onto the planet, and they turn into something like Jupiter. Now this one sits right in the middle of that, so it's really a question of, did it either sort of just slowly get to this very large mass without picking up this gas somehow, or did it become a planet like Jupiter and then lose all the gas afterwards in some sort of catastrophic event? And it's one of these two scenarios has to happen really to make the planet that we see. I mean, so the one where it never had the gas in the first place is this kind of halted formation thing, where perhaps it opened up a big gap in the disk of material that the planet formed from. And there's some theories out there that say that maybe you can open deep enough gaps that it's possible to just remove all the gas before that you've got the chance to get much of it. And then the disk sort of gets dispersed and the planet's left. But the problem with that really is that if it was that common, we'd expect to see a few more of these so far. So I'm not sure it completely answers the question. And it doesn't really tell us why the planet's in this Neptunian desert anyway. It just answers the bit about its density. So the other one, and I think some of the more interesting options really, are that you've formed this sort of planet that may be like Saturn or Jupiter or a gas giant, and then something happens to it that removes all of this gas. Now, it can be quite a rare event. We don't see these planets, right? It's the first one we've seen. So maybe, I mean, there's a few options. I mean, maybe the planet got very close to the star and was sort of disrupted by tides between the star and the planet, and that ripped away all the gas and sort of left the core as a remnant for us to see. Or one that's quite nice is perhaps during the formation and towards the end of the formation, it impacted with another planet, another forming planetesimal, they're sometimes called. And with the right sort of impact, that can blow away all that light elements in the atmosphere and leave us with a remnant core, and a particularly heavy remnant core, because you've got these two planets that collided to produce it. So that one has the advantage of sort of answering both of those issues, as well as potentially putting the planet in the desert, because it could get sort of scattered onto a very unusual orbit by an event like that. I mean, it actually leads to a few more sort of scenarios that maybe impacts are quite common. It's sort of indirect evidence that impacts can possibly shape sort of giant planet formation and their internal structure going forwards. And we've seen a few results like that from Jupiter in our own solar system as well.
So, but none of those scenarios can be proven so far.
It's hard to decide which of them can be true because you can't rule them out for sure. And we've got one example here, right? But you can say that the only one of those that actually answers all of the unusual points about this planet simultaneously is the impact scenario. The other ones all require something to happen and then followed by another event, perhaps, or some other issue. We've got this issue that the planet's in the Neptunian desert. It's super dense, and actually that it's got a very high mass of heavy elements. So this sort of 40 Earth masses worth of quite heavy material. And that's unusual. We don't expect even Jupiter's core to be anything like that massive. So if this is the remnant core of a giant planet, it's actually an unusual one in itself, and that's interesting too.
I didn't know that, because I thought by reading your paper that you have found an equivalent of a planet that could have the same sign of core. You mentioned in the paper the existence of HD 149026b.
Yes, and all these lovely names we have for planets, right?
Oh, for this one. So this, and I'm looking at my notes right now because I remember I wanted to talk about this.
So I stopped sharing the screen so we can.
Yeah, stop sharing the screen. Sorry. Yeah, so this one is this is a planet that's been discovered, I think, by radial velocity, has a mass of 120 times the mass of Earth, and you have an estimate of the core, right?
And it's sort of 50 or 60, very high.
Yeah. And so basically, so what I'm trying to say, or maybe you're gonna say it better than me, is that the core of this planet will have the same size and mass than the core than this planet you have observed, right?
Yeah, so we've observed what a planet we think is maybe the remnant core of a giant planet, something like that. But
you have to find a way to basically, as you described, to lose 60 or 70% of the mass of this planet, the envelope.
Yeah, and that takes a really catastrophic event, like an impact or, being ripped apart by the star.
And so what else? What I really like, I'm a planetary astronomer. I study planets mostly. Exoplanet is interesting because they give us kind of a window of another type of planet sometimes. And this is a very definitely another type of planet that we don't see in our solar system. So now we know we may have seen something that could be the core of a planet, of a gas giant, like a Jupiter-sized planet. That was a Jupiter-sized planet. So now you can study this, right? You can get information on the core itself.
Yeah, and that's really interesting because we think there's going to be a very small atmosphere left in this planet, so maybe a few percent of the mass. And the real question is, how does that atmosphere still exist? Because it's very close to the star. It undergoes something called photoevaporation, where it's going to lose sort of light atmosphere like that very quickly. And what we think might be happening is that what atmosphere is left is being replenished from the inside of the planet, sort of evaporated material from the core. And so it might actually be made up of material from the core. And so if we can study that atmosphere and try and work out what's in it, that gives us a really interesting direct way of studying a planetary core and the material in it. So if we can find a way of actually studying this planet's atmosphere, that'll be a really great next step forward. And one option is to try and look at the phase curve of the planet with the James Webb Space Telescope when that comes up.
That was a question from Cliff, in fact, which I've just noticed that Cliff asked exactly the question I was asking you. So the James Webb Space Telescope, which is a telescope in space supposed to be launched by 2021, will be a very useful facility. Can you tell us a bit more about the telescope and what exactly you think you will be able to do to characterize this planet?
So James Webb is a NASA facility that hasn't launched yet. It's still developing, but isn't too far away now. I mean, the first set of proposals to get time on it is this November. But so what it can do is look in the infrared, so sort of slightly longer wavelengths, right? And that is really useful for this planet because although the star is not super bright by the standards of planets that we look at for atmospheric sort of study usually, the planet itself is very, very hot because it's so close to the star. And so its infrared emission should be somewhat high. It's also orbiting in only 18 hours. So in a way, we can get a whole sort of phase curve, which is the emission of this planet over the entire orbit in a relatively efficient short space of time. Now that, by seeing what the planet emits, can start to tell us about its atmosphere. So we can try and get spectroscopy of that, try and split up that emission into different wavelength components. And that takes a lot of analysis, and we have to do the work really and see what we're likely to be able to see and actually try and get time on the facility to do that. But it's a fascinating thing to work for, I think.
So I remind our viewers that they can ask questions if they want to, but I'm going to go back to this story of the phase function because it's a bit technical. So basically, the phase function you want to collect is the phase of the planet at its orbit around its star. So it's basically you can have like the combination of the light of the star plus the light of the planet in the infrared. That will be kind of a phase of like the moon phase.
Yeah. So think of like the day side and the night side of the planet. So this planet's got a side that faces its star that's very hot, and another side facing away that's going to be probably still hot but somewhat colder. So the emission from each of those is going to be very different. So when we can see the sort of full day side of the planet, when it's actually behind the star or nearly behind the star for us, we should get a sort of peak of this emission. And when it's the other side, we'll get a minimum. And if we can look at the difference between those, we'll be able to see, especially in detail even, like how the temperature of the planet varies at different points around its surface in the optimal case. I mean, that might be too much to ask for, but we can try.
That's what they call it. The thermal. We're going to be able to measure the temperature and the thermal inertia of the core of the planet. That's
ideally. I mean, we have to see what's possible right at this stage.
Only astronomers are excited about this kind of idea.
You can look at, like, we call it latitudinal variation or whatever, how the temperature varies around the planet.
So this has been done with a Spitzer telescope like 2 or 3 years ago, if I remember. I remember these pictures.
Yeah, there's been a few cases. So 55 Cancri E is quite a famous planet for this. It's very good for these sort of phase curves of very hot, quite rocky planets.
All right. So that's we have a question, but I don't know from whom. If there were an artificial object or a former gas giant whose atmosphere were removed by artificial means, is there a method by which you could detect either scenario that rules out natural causes? So I think this question is basically, is that truly a natural cause, or is that maybe artificial cause? We work for the SETI Institute, so we have questions like this from time.
No, I mean, it's interesting to think about. I think sadly we'd never be able to tell for sure in this case, right? Because at the moment it looks like a gas giant with a stripped core, and we can think of ways that can happen naturally. So it's hard to rule those out. I mean, let alone think about how any possible civilization could do it themselves. I mean, that's an even more interesting question, really. Right?
And why the civilization will spend so much time and energy to do something like this? They should have a reason.
I mean, you could try and mine the helium out of Jupiter's atmosphere, for example, right? I mean, there's science fiction's thought about this before.
We have more questions coming. Is there a way from Rob? Is there a way from information we can gather to determine whether or not this planet is tidally locked?
So we'd be very confident that it's tidally locked, really. Anything that's that close to the star, the timescale for tidally locking is very short compared to the age of the system, which is several billion years. So I think it's almost certain that it's tidally locked, yes.
But is it tidally locked like Io around Jupiter, or tidally locked like Mercury around the Sun? We don't know. Is it 1-1 or is 3-2?
It would be 1-to-1. You'd always have the same face of the planet facing the star in this context. Just because, I mean, remember, it orbits in 18 hours, so it's far, far closer to its star than Mercury is to the Sun.
Definitely. Okay. So that's there is no more questions coming. So in the meantime, I have one a bit more like speculative about the future. So this is the first one discovered so far by tests. What will be the gain of having multiple observations? And ideally, what will be the best target for you to learn more about those kind of naked planets? Let's call it like this.
Naked cores was the name of the proposal we put in to get data on these objects even. Okay. So, nicely placed. But really, yeah, we want to target more of these from TESS. And TESS is supposed to find thousands, if not tens of thousands of planets, many of them sort of this kind of size and a bit bigger. And so being able to study all of those and do it in a statistical way so we can understand the planet population, that's really important. Because one way that we can look into how planets like this might form and how common that actually is as a mechanism for planet formation is to get an actual sample of them and see what kind of stars they occur around, how common they are, this sort of thing. And TESS is already starting to find a handful of other planets in the desert. Not quite this extreme yet, but it shows that it's not impossible to find more, and we can build up a sample like that.
Good. So you basically open kind of a new area in the field of exoplanets, a study of those.
I don't want to call it a new class of planet yet. You can't do that with just one, right? But maybe in the future.
On a personal level, how was this life, this discovery? Tell us a bit about what you felt when you discovered these, when you basically get put together the story and the publication.
Sure. I mean, well, when you start looking at these targets, you expect a lot of them to sort of go wrong. So when you're just putting them to schedule and take some more data, you sort of, it's a little bit routine. You hope things work out. Maybe they do, maybe they don't. This one, like I said, we got the first few data points and it looked like it was going to be a false positive, like an eclipsing binary or something. And so, I was looking at it, trying to work out whether this was definitely true or not. We thought, we'll get a couple more points just to see. And it turned out to be completely fine and very useful. So I'm glad we did in that case.
So it was surprising, and you have to wait to convince. How many co-authors you have in this paper? There's like 40 of
it's
them?
Nearly 100, 100 from 40-something institutes.
So, and everybody contributed, of course, right?
So many of them are the teams that put together some of these telescopes that observe it and different things like that. So you add up a lot of people by having different telescopes taking high-resolution images of the star and follow-up transits and all kinds of things. Several of the others, though, work on different kinds of exoplanet formation theory. So a lot of them come up with different ideas for how we might be able to form that. I mean, one way I went to this is we had this interesting result, this strange mass and strange radius and density. Mm. We were thinking, okay, well, how could we make this? We've got a couple of ideas, but there's some more expert people out there. So let's go around a few teams and see what people can come up with. And so we bring in people that way to try and build up a better picture and get a more collaborative approach to it as well.
Yeah, this your paper is great because it's typical Nature paper is very short, so people can read the first 3 pages basically. It's great. You learn the story, and then you can go through the details of the measurement and the characterization. And I learned a lot by reading it, in fact. And I congratulate you for making some paper which is clear and interesting enough on a new kind of target.
It's nice writing something for Nature. I think for that different format you say is very good to work with.
They force us to be concise and to get the story straight, which is great. So what's the next step in your research? Can you tell us a bit, like an insider news, something?
Yeah, I mean, well, I'm working, like I said, on these population statistics at the moment. So trying to come up with methods to automate planet discovery and further validation and confirmation in as human-free a way as we can. And like we chatted a little bit before about a machine learning algorithm we put together recently to try and do this. And we want to apply that to the test data like we have for this planet and really make a uniform sort of case study of tests and all of the different planets in it with an automated algorithm that can tell us which ones are likely to be real and which aren't, and hence look into the statistics that way.
I have a question from Agatha, which is kind of cool, a bit adjunct anticipation too. Is there a type of planet that you hope to find that has not been found yet, and what it is? What is the planet that you think we should find soon? Something exotic or something that's the goal, basically, of your research?
I mean, the goal of the whole field is to find a planet that really is like the Earth, right? I mean, something that's the same temperature, the same distance from the star, has a lot of the same properties. And there's a lot of very similar-ish things that have come out, but nothing almost exactly the same yet, I'd say. But to me as well, and people in the field, it's just really nice to see the huge diversity of planets that you get coming out. So ones like this, but there's other examples as well, like Jupiter's very close to their star and all kinds of other things. And it just shows that the universe is full of these different kinds of planets that we didn't expect to see before we started looking. And so everything exotic, I think, is a fascinating discovery just for that. Sort of mapping out the universe a little bit and giving us a bit more context of where we are.
And they challenge theorists too, because theorists always have
of course
about their models, and it's always good to show them some planets which doesn't fit into their models, so they go back to
there's always a result 2 weeks later. Someone manages to make it work.
Exactly. We have a question from Rob again. He's asking, have we ever discovered planets in orbit in other galaxies?
Not that I'm aware of, because it's very difficult to do that. Not through this transit method for sure, because the stars in another galaxy, the light's all blended in with millions of other stars at least, even in the small ones. And so it's very hard to distinguish the signal of a planet in that.
But it may come in the future with as the technology involved and we get better detector and better telescopes, of course.
Yeah, I mean, everything is possible, as I think all the results are showing at the moment.
I do remember there was a paper published like 5 or 6 years ago on the possibility of a planet around a star that thought to be a capture a star from another galaxy. A galaxy absorbed by the Milky Way, and they found the planet in orbit. But of course, we have not yet seen planet directly or detected planet directly in other galaxy, as you mentioned.
No.
All right. Well, thank you very much for your time, and
thanks to you,
David, and good luck with the rest of your research. I hope to have you again at the SETI Live to talk about exoplanets, of course. And thank you to our viewers, wherever you are. And please join us next week. I don't know what will be the SETI Live next week, but you probably know because you follow us on Twitter, Facebook. And please subscribe. Press the button on the bottom if you are watching on YouTube, and subscribe to our YouTube page. Thanks again, David.
Yeah, thanks, Frank.
Have a good evening. Bye-bye.
Bye.